Very good afternoon to all my European friends, and good evening to the Indian friends, and probably very early good morning to all my friends from North America. And I'm extremely thankful to the faculty who introduced me, Dr. Griffith, and I'm very pleased to congratulate Professor Elisabetta for the wonderful conference. Thank you for the kind invitation. And many of my students also could attend this meeting. The title of my presentation today is New Opportunities in Sustainable Nanomaterials. What I'm going to do is how we can utilize agricultural waste as a sustainable resource for production of nanomaterials. We have been active in this area for several years. I'm going to show you totality of the work we have done and some work reported elsewhere. I am right now located in India, south of Kerala, and this is my website. And you can see the emblem of my university. It's a huge university with 400,000 students. Are the slides moving now? Are you able to see the next slide? Good, the slides are moving, perfect. Let me show you a beautiful statistics of American Chemical Society. American Chemical Society gave a very interesting news. They said that 1.6 billion tons of agro waste are being produced every year across the globe. And these agro waste are not utilized properly. Most of them are getting wasted. It could be from agricultural waste, it could be from waste from fish industry. And if you look at the agro waste, you have sugarcane bagasse, wheat bran, rice bran, wood flour, variety of agricultural waste. Let me show you another important table where you will see the most important plant resource is wood. #1 in the world. Many countries focus on lots of industries based on wood. And that generates lots of waste, wood flour. Then comes bamboo, cotton lint, jute, kenaf, flax, sisal. This talk will focus more on plant-related materials, plant fibers. Plant fibers have lots of advantages. Environmentally benign materials, friendly materials, cost-effective, abundant, non-abrasive to machineries, underutilized, so many positive points for plant fibers. I request all my colleagues to have a look at this slide. Look at plant fibers could be from the stem. We call it as bast fiber. It could be from the leaf. We call leaf fiber. Good example is pineapple leaf or sisal. It could be from the seed, cotton. It could be from grass, bamboo fiber. So there's a variety of fibers. See some of the beautiful pictures of banana. We have lots of banana plantation in Kerala, my state. Lots of plantation of oil palm, pineapple. Pineapple is a very big production in Kerala. Coconuts, plenty. Kerala is a land of coconut trees. Let us have a look at the relative price of these materials, taking cotton as an index of 100. You will find that these materials are relatively cheap. fibers are quite cheap. Let me show you another slide about the mechanics of this, mechanical properties of these materials. Look at the values of tensile strength, Young's modulus, elongation at break, density. You will find that they all show good mechanics. And very important point is look at the density. Density of this material is quite low compared to glass, 1.5, 1.2, 1.1. And if you look at the specific properties, property by density, these materials can beat glass. It's a very important point. Let us look at the chemical composition of lignocellulosic material. The major component is cellulose. Very exciting molecule. You will see lots of hydroxyl groups. A chemist can do wonders on this molecule. Then lignin, a complex hydrocarbon. These are the main components of lignocellulose. Another important point I want to tell you, dear friends, you can work on different length scale. Look at this. Macro length scale with fiber. Micro length scale. So many microfibers inside this macro. And you can work on nano length scale. That's the beauty of plant fibers. The hierarchical structure is very interesting. So you can make microcomposites, microcomposite, nanocomposites. We are now, my research group is more interested on nanocellulose now. Because nanocellulose is a very exciting material. Because of crystallinity, because of strength, because of water holding capacity, specific properties. I would say this is one of the strategic platforms for sustainable development. We have now a large number of nanomaterials, graphene, CNT, metal oxides, pores, silica. Dear friends, I would say, among all this nanomaterial, I would say nanocellulose is the most sustainable platform for development. Let us have a look at the electron microscopy picture of nanocellulose. Look at this. A web of interconnected. And if you examine under your naked eye, you see this is a gel of nanocellulose. The production of this nanocellulose is matured now. We can produce by acid hydrolysis, steam explosion, high intensity ultrasonication process, cryo crushing process, super grinding, high pressure homogenization. So variety of techniques to be applied for the manufacture of nanocellulose. Look at high pressure homogenization. You include passing the cellulose slurry at high pressure into a vessel to very high velocity. That creates a lot of shear forces, and that shear forces decrease the size of fibers. This is what is high pressure homogenization. You can also make by super grinding. Professor Abe and group worked on this super grinding in Japan. By crushing, you cool the material. You allow the nanocellulose to be solid in water, then you subsequently go to sub-zero temperature and you apply a high shear force. You can produce by high cryo crushing. You can produce by high intensity ultrasonication process. Again, it's a mechanical process in which oscillating power is applied so that you can attain nanoscale. Steam explosion process, you subject everything under high steam. Pressure is 137 Pascal, alkaline atmosphere, alkaline conditions. Temperatures could be around 150 degrees Celsius. Then you suddenly release the pressure, then you have an explosion. You can see because the explosion, the cellulose is opened up and the lignin hemicellulose are removed by chemical hydrolysis. This is what is steam explosion. So let us see what I do in my laboratory with my group members. My PhD students collect the agricultural waste from the plantation. They clean it, wash it, chop it into small fibers, and then they do an alkali treatment, remove lignin and hemicellulose. This is again a very important material. You get a slurry, you go for acid hydrolysis coupled with steam explosion. You can use mild acid or strong acid. If you want to have nanocrystals, we go for strong acid. If you want to have long nanofibers, we go for mild. Dear friends, eventually, you know what you get? You get beautiful nanofibers. If you use strong acid, you get nanocrystals. You can differentiate this from this picture. See, this is nanofiber, long nanofiber, where you have crystalline amorphous phases coexist. If you remove all these crystalline entities, amorphous entities, what you get is you get short nanocrystals. Short nanocrystals. So you can make either long nanofibers or short nanocrystals. The beauty of this material is, look at the modulus, 130 gigapascal. Look at the strength, 10 gigapascal. Typical polymers, the modulus is 2 or 3 gigapascals. You can have by putting this material into polymers. Look at their low force, regular shape, high axis ratio. Look at these nanocrystals made by Muhammad, by strong acid. He used sulfuric acid, 65%, 45 degrees Celsius. Muhammad made beautiful nanocrystals from wood flour. Now let me show you what I do in my laboratory. In my laboratory, my PhD students collect the agricultural waste. It could be sisal or it could be pineapple. We remove all the stuff and get the fiber, pop into smaller lengths, subject to steam explosion process, bleaching, acid hydrolysis. Finally, we get beautiful nanofibers. I wanted to show you the dynamics of the enrichment process. Dynamics of the enrichment process. The raw fiber has a cellulose content of 64%. Raw fiber has a cellulose content of 64%. And as you feed this fiber by acid, you get quite high amount of, at the end of the day, you get something like 95% of nanocellulose. And you remove hemicellulose and lignin. Just to show you the enrichment process. You remove lignin and hemicellulose progressively. I want to show you another very interesting slide of my former co-worker. He's right now in the US doing a postdoc. He made beautiful work. He made lots of nanocrystals from banana stalk. He collected the banana stem from the agricultural plantation and went for acid hydrolysis, strong acid. He made beautiful nanocrystals. Let me show you another work we did with the University of Luleå, where my PhD student went there. We had a long cooperation with the Luleå. This was from wood flour. Look at this. Atomic force microscopic picture of wood flour, where we have made nanocellulose of wood flour. Look at another work we did with Brazil. We had a long Brazilian collaboration. So my PhD student made nanocellulose from pineapple leaf fiber. An FESCM picture. Pineapple leaf fiber. So we are able to make beautiful nanofibers and nanocrystals from all these agricultural waste. We are able to characterize them well. Let me show you another important slide. A chemist can do a lot of chemistry. You can go for tempo oxidation process where OH could be converted into OH. You can do esterification reaction. You can graph different types of monomers on the surface, polymer grafting. You can introduce fluorescent labels on the surface of nanocellulose, and you can do a lot of fluorescence spectroscopy work for sensing. You can do cationication reaction. You can do cellulation reaction. So several reactions could be performed on the surface of nanocellulose. Let me show you what are the important applications of nanocellulose. This could be utilized for water purification. This could be utilized for wound healing application. This could be utilized for EMI shielding. This could be utilized for EMI shielding. This could be utilized for wound healing. And so variety of applications we can have. I will show you one by one. One is water. You know, water is a very important material. And the amount of drinking water is decreasing. Even says that many parts of the world will have tremendous scarcity of water. Therefore, it's every need to have sophisticated, cheap separation process, purifying water. So we thought of utilizing nanocellulose for purification of water. You know what we have done, my PhD student looked at the commercial filters. Commercial filters are bilayers. Look at the commercial filters, you have a base which is non-woven micro support, above which you have an electrosponge system. Electrosponge system is mostly PVDF. It's a bilayer. This is a commercial filter construction. So we thought of modifying the commercial filters. You know what we did is we gave a nanocellulose coating on the surface of the commercial to remove dyes, nanoparticles, heavy metals, bacteria, and viruses. Probably you all know that water is increasingly contaminated with the different types of dyes, particularly coming from textile industry. Textile industry uses lots of dyes. And we picked up some of them. One dye we tried to remove was crystal violet dye, which is very much used in textile industry. You know what my PhD student did? This is a structure of cellulose. He modified nanocellulose with meltron acid, green chemistry. And he could introduce CO minus group on the surface of nanocellulose. This sort of chemistry we have done in the laboratory. Simple chemistry. And see the efficiency of separation. This is the normal commercial filter that you get from the market. Absorption capacity as a function of time. You see the film capacity is not good, not very good. But if you give a coating with the nanocellulose, which is unmodified, no chemistry on the surface, you need nanocellulose coating. Of course, the separation efficiency has been increased. But if you use chemically modified nanocellulose, you see where we stand. We have something like 4 milligram per gram efficiency. Commercial filter is having something like 1.2. So you have a very good increase. And you might ask why this happens. Look at when you pass water through this filter, all these dyes, crystal violet dye molecules are being separated by the filter. And when you do a chemistry on the surface of nanocellulose, you have CO minus group. And the CO minus group can have electrostatic interaction with crystal violets. And this electrostatic interaction really helps to remove crystal violets from the impure water. Now let me show you another interesting thing what my PhD student did. Probably you all know that water is increasingly contaminated with lots of suspended particles. It can be nanoparticles, microparticles. What we did is, we tried to pass all this impure water through the filter. And dear friends, when you give a coating, the nanocellulose on the surface of this filter, the pore diameter, the pore size, the pore diameter is something like 8 nanometers, so small. So most of the suspended particles could be retained on the surface. Look at this. I will show you a separation picture. All the suspended particles in water will be retained by the top of the filter, where you have a coating with nanocellulose. And the base is nothing but electrospun PVDF. Look at this. All this are being retained by the top. Of course, you have to clean this filter to be used. Look at this filtrate. If you look at the feed solution, this is completely opaque. And the filtrate is very clear. You see the transparency of the filtrate. So we are able to remove suspended particles. Let me show you a very interesting work of Finnish group, Finland. They're very active in nanocellulose. What the Finnish group did is they made aerogel. See, look at the aerogel made by the Finnish group. Manufacturing of aerogel is quite simple. And then they made aerogel. And then the surface of aerogel has been made hydrophobic. How would they do hydrophobic property? They gave a coating with titanium dioxide. Look at this. They made aerogel by freeze drying. And then after freeze drying, they gave a coating with titanium dioxide. So this aerogel became highly hydrophobic. Doesn't like water because it is coated with. You sprinkle this in seawater. You know, seawater is now increasingly contaminated with oil. Lots of ships sink in sea. Water is increasingly contaminated. So when you sprinkle this in seawater, what happens? All the oil is absorbed by this hydrophobic aerogel. Oil is hydrophobic. It cannot absorb water because surface hydrophobic. Look at this. Water is sticking on the surface, but it cannot be penetrated. And this red is oil, so all the oil is taken up by the aerogel. And you can burn it or you can reuse it. This is one way of an efficient way of purification of contaminated oil. Let me now show you removal of heavy metals. Look at India, the northeastern part of India, where we have lots of heavy metal in drinking water. And people use different types of filters to remove that. You can make use of nanocellulose to remove heavy metals. Look at this chromium 6. If you want to remove chromium 6, which is negatively charged, what you do is you do a small chemistry. You react nanocellulose to the polyvinylamine. When you react to the polyvinylamine, you make the nanocellulose surface electropositive. You use a lot of amino acids. And the negatively charged chromium 6 will be charged by electrostatic interaction. You can look at this. You see the trapping of chromium 6. You can remove nickel, you can remove cadmium, you can remove lead. Several metal particles to be removed. They're all by electrostatic interaction. You can also remove bacteria and viruses. You can remove bacteria and viruses. Bacteria by a size exclusion principle because the size is big. And virus, we are actually troubled by this corona pandemic. My country is very much affected. Italy was affected. The whole world is affected by it. We can also remove viruses using this platform. You want to remove bacteria and viruses. Bacteria, simple, they're big. By a size exclusion principle, you can remove because they could be retained by the filter. They're bigger in size. But if you want to remove viruses, they're small. You need to have some chemistry. Simple chemistry, polyvinylamine is the best. You introduce positive charge on the surface of nanocellulose. Put amine function group on the surface. Probably you all know that viruses, including coronavirus, has a protein envelope, a negative charge. And you can trap these viruses by electrostatic interaction. So this is again a good way of removing bacteria and viruses. Nanocellulose is a good platform for regeneration of cells. You can see gentlemen suffering from high degree of burns on his face, and his face is covered with gel of nanocellulose. Nanocellulose is extremely porous. You can see from this microscopic picture. And when you apply this gel on the surface of the burned skin, regeneration of the cells are so rapid and so big. It is an excellent platform for burns, regeneration of cells. Let me show you another important work we have done with Sao Paulo University in Brazil, because we had a long cooperation with them. My Brazilian counterpart is very active in making polyurethane for look at the PU made by my Brazilian colleague, the strength, is the modulus. We thought of reinforcing this by cellulose nanocrystals produced from pineapple leaf fiber. See, look at this slide. If you put 5% of nanocellulose, the strength becomes 52.6. And you see a quantum jump in modulus, 37.5 become 992.4. Remarkable increase of. You know what my Brazilian colleague did? He made very interesting nanocellulose, polyurethane, prosthetic heart valve. He did lots of experiments with the Brazilian hospital. Before that, he made lots of studies. Animals. Eventually, he was successful in making this nanocellulose, polyurethane, prosthetic heart valve. This is an excellent platform for wound healing application. Excellent platform for delivery of antibiotics, sustained release of antibiotics. Maybe I'll show you a very beautiful slide by work by Sebastian. Sebastian introduced, he made nanocellulose, aerogel, introduced antibiotic into this platform. Octinidine, introduced octinidine, and looked at the release profile of octinidine. Sebastian said you can have beautiful sustained release of antibiotic from this platform. Professor Liu did something very interesting. What Professor Liu did is, Professor Liu combines nanocellulose and collagen together. When you combine both nanocellulose and collagen, you get a wonderful platform which is extremely biocompatible. He made aerogel. Look at the aerogel made by Professor Liu. And density of this aerogel is 0.02 to 0.03 gram per centimeter cube. Very, very light. Porosity is between 90 to 95%. And look at the water absorption capacity, 4,000%. And Professor Liu said, this is an excellent material for wound dressing. because it can absorb all this water. It's extremely porous. Another important point I want to tell you is, you see, most of the filters that you get from the market, commercial filters, are usually made by electrospinning process. You can see a PAN, polyacrylonitrile, the blue color, which is made by electrospinning. Look at the mechanics. You have a 4 MBA strength. Dear friends, we want to increase the strength of this material. You give a coating with nanocellulose. Look at this one-side coating. The strength becomes 10 megapascal. Both side coating, the strength becomes 13 megapascal. So you can increase the strength of commercial filters by coating with nanocellulose. Let me show you something we have done during the Corona time. We made an NSO program with National Science Foundation in the US and many universities in India and Georgia Tech in the US, in Atlanta. What we proposed is, we proposed a tri-layer mask. Tri-layer mask. The outer layer is actually made of polyester coated with an anti-adhesive layer. The outer layer that can repel coronavirus because the surface is hydrophobic. The coating of anti-adhesive polyelectrolyte. The middle layer is a very interesting concept. The middle layer is electrospun, nylon, engraved with nanocellulose, with a little bit of curcumin. This is a middle layer. Innermost layer, which is close to your mouth, is made of cotton. So this is a tri-layer configuration. So this outer layer can drive away the coronavirus because it is anti-adhesive, highly hydrophobic. If at all some coronavirus get in, if you're careless in wearing the mask, this middle layer can kill the coronavirus because it has positively charged nanocellulose. This positively charged nanocellulose can interact with the negative charge on the virus. Virus could be deactivated. You can remove the coating layer. The innermost layer is very comfortable coating. It is in contact with your mouth. This is our configuration of our mask: the outer layer, the middle layer, and the inner layer. We also propose to make it by 3D printing. Now let me show you some more interesting slides where you can use it for sensing. You can mix nanocellulose and CNT together, and put into natural rubber latex. Or for a compression molding, you get beautiful nano composite of CND and CNC. This is a quite interesting observation. If you look at CND alone, CNT natural rubber nano composite, look at that, you get a percolation at more than 6% of CNT. That's not very interesting. But if you combine nanocellulose and CNT together, look at what you get. The percolation could be shifted to lower concentration of CNT. You get beautiful percolation at 1.2 volume percent of nanocellulose. And this is a very interesting material for sensing. You can hybridize with the graphene, because for the time I'm not going to show. You can hybridize with graphene, hybridize with so many.
You still have 5 minutes maximum.
Yes. Now, I'm going to show you another interesting work. A PhD student of mine, Mr. Dibu, he has made nanocellulose by hydrolysis. And then he mixed it with aniline, he polymerized, and then he has made in situ polymerized polyaniline cellulose nanocomposites. Look at this. Very simple process. You can see that the totality of the process. Nanocellulose dispersion, aniline is injected, you have in situ polymerization, vacuum filtration, you get flexible, you get very flexible nanocell paper. It is extremely conductive. And what's the use of this material? Look at the conductivity. This is a very valuable material for EMI shielding application. Fantastic material for EMI shielding. I can also a couple of slides on. We are also active into chitin chitosan, extracted from calf shells. You see, we can make either chitin nanocrystals or nanofibers. Acid washing and steam explosion. I will show you one work. If you look at the nanochitin is essentially hydrophilic. This is a structure of nanochitin. A lot of hydroxy groups. And you can introduce alkyl group on the surface of nanochitin by a simple chemistry. You react to the bromohexadecane, then you can have this sort of alkyl group. If you put an alkyl group, the chitin becomes hydrophobic. You look at this. This is the nanochitin without any chemistry. 86.5, the contact angle. If you put alkyl group on the surface of this chitin, you can achieve 158.2 contact angle. You can make super hydrophobic surfaces. That's a fantastic material for structuring of the oil. You can add this into oil to control the viscosity. Recently, we did some work on combining combining chitin and PVDF. The commercial filter, if you look at PVDF alone, and if you want to remove some dyes from water, indigo carmine dye, we have tried. So removal efficiency is something like 23%. PVDF alone. If you combine PVDF and nanochitin together, look at the removal efficiency becomes 88.9. So chitin is also a wonderful material for environmental remediation process. This we have done recently with a university in Slovenia. We are also into waste starch. My PhD students collect all the waste starch, waste potato, waste rice, waste wheat, waste cassava. We don't touch the food sector at all, but we touch only the waste. We can make wonderful nanocrystals from starch. See, thanks to Alan Dufresne, he is the master of this. He made lots of beautiful nanocrystals. Acid washing, you get beautiful nanocrystals. And I will show you a very interesting work of my former coworker. We made nanocrystals from potato starch, waste potato starch, and mixed with natural rubber latex. Look at the mechanics. This is neat natural rubber. An increasing concentration of nanocrystals made from starch. The modulus goes up, the strength goes up, and you see a sort of cartoon we have made. Nanocrystals form a network inside natural rubber. And natural rubber molecules are immobilized by this nanocrystals. Dear friends, I'm going to conclude my presentation. Agro waste could be a wonderful starting material for a large number of advanced functional materials. Nanocellulose could be utilized as a reinforcing filler, water absorption, wound healing, energy storage, EMI shielding. And nanochitin again is a very nice material for environmental remediation, structuring of oil, metal removal. And waste starch is also quite interesting. You can make nanocrystals from waste starch and use as a reinforcing material. I am posing a question to all my friends. Can we become a zero waste planet? We have to intelligently utilize all this waste, transform into beautiful. I would like to thank my co-workers. Funding from Government of India, particularly thankful to Professor Sena Rao, the Nano Mission Chairman, all the funding agencies, international collaboration from France, India, Sweden, India, Slovenia, to us, India, Brazil, DuPont, many companies, And my collaborators from Brazil, India, France, Sweden, we have a large number of collaborators across the world. This is my group in chemistry. I have a group in chemistry. This is my group in chemistry. You can see my collaborator from France visiting me, Alain Dufresne. Sorry, Yves Grohens. And my group in nanoscience and nanotechnology. You can see the present director of the group. And we a good group of nanos. And most welcome to India after the pandemic. I am from this region, Kerala, the Goson country. You have beautiful, some beautiful pictures of Kerala. We have very nice canals. Houseboat, you can live in this houseboat and you have beautiful fish, very tasty fish. Boat race, dance of young girls and very, very old temples. Please do visit me after the pandemic. This is my campus. And we have a conference coming up, International Conference on Macromolecules, September 10 to 12, 2021. Online conference because of the pandemic. And I'm also the editor of Nanostructures and Nano Optics. Those who work on nano, please submit your articles to Nanostructures and Nano Optics. Elsevier, traditional journal, no fee. Thank you so much for your patient hearing. Thank you.
So thank you, Professor Sabu. It was very interesting. So many things, so many work. And we have one question from Mohamed Cheimi in Paris, in CNRS. So he told us thank you for sharing knowledge of agro-waste derived smart materials. And concerning heavy metal ions, how do you address the crucial issue of selectivity, for example, in the removal of metal ions?
Very interesting question. We have not really looked at the selectivity of this material. See, suppose we want to have chromium 6. Chromium 6 is interestingly, negatively charged. So we made the surface electropositive. And suppose you have metals with a positive charge. Nanocellulose, which is made from acid hydrolysis, are intrinsically negative charge. So all these metals are trapped by electrostatic interaction. So we have not really looked at the selectivity of this metal. That's also we will be looking at. Selectivity of this metals also could be done by the degree of, electrostatic interaction. So we are looking into that aspect. It's a very interesting question. How do you manage selectivity of this material?
Okay, thank you. I have another question. What is the limit size of nanoparticles that you can absorb with your materials?
You see, if you look at if you count on the surface of filters, the whole size is 5 to 8 nanometer size. So all the particles above 10 nanometer could be retain the surface of the filter. Look at all the suspended particles. You could retain all of them on the surface. And we are able to engineer the pore size quite beautiful way.
Okay. So thank you.
Thank you so much.
Thank you.
Have a wonderful conference.